So far, the only collection type we've dealt with was the list. In this session, we are going to make a tour of other kinds of collections which differ from lists both in their functionality and in their performance profile. One thing will stay the same, however. All the collections that we are going to study in depth are going to be immutable. We are going to start in this session by looking at different kinds of sequences. We've seen that lists are linear. Access to the first element is much faster than access to the middle or end of a list. The Scala library also defines an alternative sequence implementation called a vector. This one has a much more evenly balanced access pattern than list. Vectors are essentially represented as very shallow trees. To see how that works in detail, let's make a little drawing. So a vector of up to 32 elements is just an array, where the elements are stored in sequence. Here I only draw 4 for simplicity, but in practice it would go up to 32. Now if a vector becomes larger than 32 elements, its representation changes. What you do then is you would have a vector of 32 pointers to arrays of 32 elements. So again, I only always abbreviate to 4. And once that is exhausted, so once we have 32 times 32, so it would be 2 to the 10th, 1024 elements full, then the representation changes again, and it would then become a vector of pointers to arrays of 32 elements. So everything would become one level deeper. You see what the principle is. So a vector with 3 levels then would go up to 2 to the 15th elements. A vector of 4 level, 2 to the 20th. 5 level would give you 2 to the 25th, and 6 levels would give you 2 to the 30th. That is 1 billion elements, and that's about as far as it can go. So let's analyze how much time would it take to retrieve an element at some index in that vector. We've seen for lists it very much depends on what the index is. Fast for 0, slow, linearly slow for indices towards the end of the list. For vectors are much better behaved here, because to get an index of a vector of length 32, it's a single index access. If the vector has size up to about 1000, then it's just 2 accesses. So generally the number of accesses are the depth of the vector. And we'll see that that depth grows very slowly. A depth of 6 gives you 1 billion elements. So generally the formula would be that the depth of the vector is log to the basis of 32 of n, where n is the size of the vector. So we've seen that log to the basis of 32 is a function that grows very slowly. That's why vectors have a pretty decent random access performance profile, much better than lists. Another advantage of vectors is that they are fairly good for bulk operations that traverse a sequence. So such bulk operations could be, for instance, a map that applies a function to every element, or a fold that reduces adjacent elements with an operator. For a vector, then, you can do that in chunks of 32, and that happens to coincide fairly closely to the size of a cache line in modern processors. So it means that all the 32 adjacent elements will be in a single cache line, and that accesses will be fairly fast. For lists, on the other hand, you have this recursive structure where essentially every list element is in a const cell with just one element in the pointer to the rest, and you have no guarantee that these const cells are anywhere near to each other. They might be in different cache lines, in different pages, so the locality for list accesses could be much worse than the locality for vector accesses. So you could ask, if vectors are so much better, why keep lists at all? Well, it turns out that if your operations fit nicely into the model that you take the head of the recursive data structure, that's a constant time operation for lists, whereas for vectors you have to go down potentially several layers. And then to take the tail, to process the rest. Again, a constant type operation for lists, whereas for vectors it would be much more complicated. In that case, definitely if your access patterns have these recursive structures, lists are better. If your access patterns are typically bulk operations such as map or fold or filter, then a vector would be preferable. Fortunately, it's easy to change between vectors and lists in your program because the two are quite analogous. So we create vectors just like we create lists, only we write vector where we had written lists. And we can apply all the same operations of lists also to vectors, map, fold, head, tail, and so on, except for the cons, because cons in a list, that's the primitive thing that builds a list and lets us pattern match against the list. Instead of a cons, vectors have operations plus colon, which adds a new element to the left of the list, and colon plus, which adds an element to the right of the list. So you see these here. X plus colon xs creates a new vector with leading element x followed by all elements of xs, and xs colon plus x creates a new vector with trailing element x preceded by all elements of xs. So note that the colon always points to where the collection is, where the sequence is. So let's see what it would take to append an element to a vector. Again, vectors like lists are immutable. I can't touch the existing vector. I have to create a new data structure. So what I would do is I would take the last array here and create a new one which contains the given element. If the vector is completely full, I would have to create a new level, but I would assume that there's still space left in the arrays. So that gives me a new array of 32 elements, which I then have to combine somehow with the original vector. I can't change the pointer from the original root to this array, because that of course would change the old vector. So what I do instead is I create another copy here that points to this new element, and it also points to the other elements that my previous copy pointed to, and that then would replace this one here. And finally, I need to create another root which points to my new copy and to the other immediate descendants of the root, and that finally would complete the construction. So the new vector now is in red, whereas the blue one wasn't touched at all. So if we analyze the complexity of that, then we see we have to create a new object, 32 element array, for every level of the vector where we did the change here. So in our case here, 3 of these arrays would be created. Not as efficient as changing a thing in place, but we get something in return. We get really 2 copies of the vector that are both completely functional and that are not in each other's ways. So the complexity again is here, if you analyze it again, log 32n. But now it's object creation. So we create as many objects of width 32 as we have levels in the tree. So vectors and lists are 2 implementations of a concept of sequence, which is represented in fact as a base class of list and vector. So if we do a diagram of the collection classes, then what we would have here we have class list, here we have class vector, and the 2 are subclasses of a class called sequence. There are other collections in the Scala library as well. So besides sequences, we would also have sets, which very much resemble the sets that you had looked at in your various homeworks, with a bit more functionality. And we'll also see a structure called a map. So these will be covered in future sessions. Sequences, sets, and maps are all instances of a common base class called iterable. So that's the start of the hierarchy of Scala collections. In fact, there are also some other things in the Scala library that look like a sequence. Arrays and strings both support the same operations as sequences, and they can be implicitly converted to sequences where needed. So to demonstrate that, let's go in the worksheet. I've defined an array, again analogous, I've just written array instead of list. And if I do that, then the worksheet would respond that I have defined an array of int, and here are the elements of the array. What I can then do, I can, for instance, apply a map function, just like I did apply a map for lists, and I would get the array with every element doubled. Another sequence-like structure is a string, so let's define one. And we can then apply, for instance, an operation like filter, which gives us all the uppercase characters in the string. So this would give us just HW. So you see that the usual operations on sequences like map or filter or fold or head or tail or take while and so on, they all also work for arrays and strings, which is quite handy sometimes. So going back to our diagram, we would then have a string and array as further sequence-like structures. I draw a dotted line here because they're not really subclasses of sequence. They cannot be that because both string and array come from the Java universe, and of course a Java class that doesn't know that at some future time somebody would define a class called Scala.sequence. Another simple and useful kind of sequence is the range. A range simply represents a sequence of evenly spaced integers. The three common operators to construct ranges, I can write 1 to 5, and that would give me the range of elements 1, 2, 3, 4, 5. I can also use 1 until 5. The until operator is exclusive in the upper bound, so the sequence would only go from 1 to 4. And I can also vary the step value by the by operator, so I could write 1 to 10 by 3, and that would give me the range of 1, 4, 7, 10. Or the step could also be negative, so 6 to 1 by minus 2 would give me the sequence 6, 4, 2. Of course, ranges are not represented like arrays or vectors as sequences of elements. There's a much more compact representation. All we need to store for a range is the lower bound, the upper bound, and the step value. And these three values are just stored as fields in a single range object. So coming back to my diagram, then I would have one more implementation of sequence called a range. So now that we have sequences, it's time to look at some more operations that exist uniformly for all sequences, including lists and vectors and ranges. The first operation is exists. So XS exists with the predicate P. This gives us true if there is an element in the sequence XS such that the predicate P of X holds. Otherwise it would give us false. The dual of exists is for all, so that one would return true if P holds for all elements in the sequence XS. So if we look at the worksheet, for instance, S exists, C is upper, would return true because in fact there are two uppercase characters in the string, whereas if we ask whether for all elements character is an uppercase character, we would expect to see false, because there are also lowercase characters in the string. Another useful operation on sequences is one that takes two sequences and returns a single sequence of pairs of corresponding elements of the two sequences. That operation is called zip, like the zipper that takes two single strands and combines them into a strand of pairs. So to try that out, let's create a sequence. Well, pairs equals, let's create, let's say, a list of 1, 2, 3. Zip, well, let's take our string S. What would we get here? Well, we would get a list of integers and characters that contains the three elements 1H, 2E, 3L. So we have taken corresponding elements from the two sequences and put them into pairs of the result list. The dual of zip is unzip, so if we do a pairs.unzip, what we will see now is a pair of two lists. The first list contains the first half of the pairs that we've seen, 1, 2, 3, and the second list contains the characters from the second half of the pairs. Good, so we have seen exists to unzip. The next useful function is called flatmap. It takes a collection XS and a function f that maps each element of XS to a collection by itself. And it would then concatenate all the results collections into one large collection. So let's see that in action in the worksheet. We could apply following flat map over a string. So it takes a character in the string and it would give us back, let's say, a period followed by the character. So each character in the string gets mapped to a list, but flat map would then concatenate all of the lists in a result collection. Let's see how that would work. So what we end up with is in fact another string that now has a period in front of every character of the original string. The last group of operations I want to cover are some utilities for ordered or numeric collections. So if you have a collection of numbers, we can take the sum or the product of that collection. And if you have a collection of ordered elements, we can take the maximum or the minimum. A quick test here. So xs.sum would give us 50 and xs.max would give us 44 as expected. So let's apply these new operations to some examples. The first thing I want to do is I want to list all combinations of numbers x and y, where x is drawn from one interval, let's say from 1 to m, and y is drawn from another. So what I would do is I would cycle through the list 1 to m, and I would do a flat map with, what would I have to do here? Well, it would be, I have to go now through the second list, 1 to n, and I need a map. So for every element in 1 to n, I return a pair that consisting of x and y, where x is drawn from the first range and y is drawn from the second range. So the next example to look at is scalar product. So the scalar product of two vectors is the sum of the product of corresponding elements xi and yi of the two vectors. And we can take the mathematical definition and map it directly to code. So what we do is we first zip up the xs and the ys, that brings corresponding elements together into pairs. And then we have a map that performs the multiplication on each pair. So we have a pair xy, we pull out the first half, we pull out the second half, and we multiply it. And finally, we need to take the sum of the results of the multiplications. There's actually another way we can write that using a pattern matching function value. So instead of pulling out the elements of the pair with the selectors _1 and _2, I can also use pattern matching on a pair. So here's how that would be written. I have again the xs zip ys, but then I map with a function that reads in braces simply case xy, so it's a pattern match against the pair, which will always succeed, by the way, because I know that I get a pair, and then simply return x times y. So that generally is a shorthand for a match expression. So the function value that consists of one or more cases in braces is actually exactly the same as a function value that takes a parameter and then matches on the parameter with the cases as they are given. Of course, the first version is shorter and probably also clearer than the second one. So here's an exercise for you. You know that a number is prime if the only divisors of the number are 1 and the number itself. What's a good high-level way to write a test whether a number is a prime number? For once, I want you to value conciseness over efficiency, so I want you to express the test in the most abstract and mathematical manner possible. Don't worry about its efficiency. So we would have a test is prime, it takes an int and it returns a boolean. And how would we define it? So to answer that quiz, simply look at the mathematical definition and translate it directly into code. So if a number is prime, if the only divisors of the number are 1 and the number itself. That means for all other numbers between 1 and n, that number is not a divisor of n. So let's just express that here. So all other numbers between 1 and n, that would be the range 2 until n. And then there's a for all that should hold for all of these numbers. We give it a name, let's call it d. So what should hold is that n modulo d leaves a rest which is different from 0. So that's a very high level and short definition of what it means for a number to be a prime number.